Hi and welcome back to the lab. And today here on the bench we have a FT-847 from Yaesu, and the radio came in with the fault description that it is totally off frequency, and especially noticed on SSB, and the owner told us that he is not really able to use the radio on SSB. So we need to have a look at it and let's see what we can do. Okay, and let's go into it. And I've already dialed the radio to the 70 centimeter band because we all know that as high as the frequency is, as higher our potential error is. So if there is really a problem, we will definitely find it first on the highest frequency, on the highest band the radio dial to, and therefore that is the right frequency. And so I'm sending already in the radio, and we see we have almost S9 level. And if you are listening to the received tone, if your ears are trained, you already can hear that that is not a 1 kilohertz tone. So we definitely recognize that our radio is off, and we can prove it as we see our radio communication service monitor. And here on the screen we really see what it is. So here we have our received frequency when we send with really 1 kilohertz audio tone. Okay, so that is what we receive back, and we see it is only 580 something hertz, which is of course totally off. And when we talk about SSB, that really matters. And do not confuse by here our 2 meter frequency, because I'm using this here for transmission, and therefore I'm only using here the part, the audio analyzing part, for seeing what's going on here. Okay, and that means let's transmit into the radio, and let me first do it on FM, because as we all know, then we have a carrier. So I've set the radio to FM, and let's see what we get. So when I now press PTT, we should really see 438,700. Now I'm transmitting with 16 watt, as you can see, and we see it is 700 but 5.5, and that is 550 hertz. So let's make it more accurate with our counter. Okay, and I've tried to get both in. So let's now press PTT again, and we definitely see that the radio is 540 hertz off, and that is even too much for FM. But to be sure that everything is fine, let's do here the same on SSB. So radio is set now to upper sideband, so that means SSB obviously. And we know if I now press here the PTT, that would not show anything up, because we do not have really an carrier. So therefore we need to feed in a tone, and therefore I use my audio generator, which we have here. And you see, let me zoom it in a little bit more. So what we can see, I've set it to 1 kilohertz, so that is a tone we are dealing with, and I've set it here to 50 millivolt RMS, so that will be the level which I feed in directly into the microphone. And then let's see what the impact will be on SSB. So we should then see, of course, our 438.700 megahertz. So that is the RF frequency, of course, and we add with our audio generator 1 kilohertz to it, our audio frequency. And that means we should see on our counter 438.701. So then our 1 kilohertz audio tone will be represented in our RF signal. Okay, everything is prepared here for SSB, and of course you may hear the tone, which is completely off. Now let's transmit with our audio frequency tone. So now PTT, and what you see is 438.701, which is fine, but then you see we are 400 hertz off. 400, come on, a little bit too low the level here maybe. 405 hertz off, and that means that we really have to look after it, because maximum 30 hertz on SSB will be tolerated. All huge or all bigger error, maybe that is the right wording, will lead to a not understandable sound on air. So we have to fix it. So let's see what's really going on here. And for all who may wonder how I can feed it in, microphone, put it here onto the speaker, press PTT, and you see that there is a signal going out. If I take it away, so no power, back here to the speaker, and it is not really loud, but it is enough here to drive our radio. So that is everything you need to do. Very easy. But now let's crack open the radio and let's see what's really going on here. Okay, the lid is off. What I want to show you is that obviously somebody was already in, so you can see it here at this copper piece what here is over it. So that indicates that already somebody was in, so that is very important to know. You should always watch for indications that somebody else was already in, so that might help to identify faults. Okay, and whenever we have to deal with a frequency off, then we have to consider first our reference frequency. And what we see here on our block diagram, let me enlarge it here a little bit more. We can see that we here have our reference oscillator, which is on 22.625 megahertz. 22.625 megahertz. That is the oscillator, and what we see here is that we then have a frequency doubler x2, and that is a reference frequency which goes out to our PLL circuit. And it is clear, if we have here a doubler, that we need here at our ref output 45 250 megahertz as reference frequency for our PLL circuit. And what we see as well, if our reference frequency is not okay, our second LO, which is definitely also fed here by the reference frequency, we see that then our mixer gets the wrong frequency as well. So the second mixer, if you like, it is not from the first LO, that is already the second LO, and everything in the radio depends here on our reference crystal, and if that is not fine, we have a problem. And looking here onto the board, we see down here, so let me go a little bit closer. So you see here a crystal which is the X1001, and that is our reference crystal. And you see that it's not a TCXO or it is either not an oven controlled, so that is a very simple crystal, and that makes it even more important to have a good alignment. If the alignment is off, it will then subsequently have impact on the frequency on our radio. So we really need to know now what is the output, so the reference output frequency to our PLL circuit. And what you see down here, so that here is our reference output jack, and I've already here connected my test lead to it, and I monitoring here our reference frequency, and I'm monitoring it on my counter. So let's see what we find. And here is the frequency which we see when we monitor the frequency from the reference oscillator. And do you see what's going on here? So we have, of course, our 45-250 megahertz, what we need, but what we also can see that our frequency is off 44 hertz. And now you may think, oh, okay, 44 hertz, so that is not that dramatic. But it is, because remember, our reference frequency is only on 45-250 megahertz, but we operate the radio on 438, so roughly on 440 megahertz. So that is 10 times our reference frequency. And now you may see the impact. If already our reference frequency is off only 44 hertz, that means 10 times more here, that is then 440 hertz. And remember, when we tested on our 70 centimeter band, we saw that we had a problem or an error of about 450 500 hertz, which our frequency was too high, and that is our 10 times higher than our reference frequency. So you see, it is absolutely important that you get your reference frequency really as close as possible, because if it is only a bit off, you always have problems. First on SSB, of course, because on SSB it matters much more than on FM, right? And then as high as the frequency is, as more the error will impact. So therefore, let's try to align this frequency as best as possible, and then we know that not only the reference frequency itself is better, as well we have then the right second LO, which is very important when we are in our receive line, right? So that is then subsequently even more accurate, which will then lead, of course, to a much better frequency stability. Not really stability, but to a better frequency set, if you like, and thus it is then more on frequency. Well, and as I already said, we only have here a very normal crystal. So it is already a problem that the lid is off, because the temperature now is different to what we have if the lid is over. So what I try now to do, I try to align it, and you see that is here a capacitor trimmer, a trim capacitor, and I try to align it as best as possible, and then we have to put the lid over it. We have to wait until it is heated up again a little bit more, and then maybe we need to realign it, and hopefully we can get it better on frequency. But if that doesn't help, then that is always the point where you have to think about the T6 or such, because then you have directly a better frequency stability. So well, therefore let's try what we can do. Okay, and you see now I have improved it very much, which looks pretty good. But as I told you, now I put the lid over it to try to get it a little bit better on heat or on temperature, and then let's see if it is still that good as we can see it here. So we go back and control it, I would say another half an hour, where I put of course here my lid on. And that is what it looks like. So now here is our test wire, and now let's wait until we see if it is moving or not. But what you already may see, if you need an absolutely correct frequency standard, because otherwise you are really in trouble. You never will get it on frequency. So therefore it is essential to have a really high quality standard for doing jobs like this. And of course on the second hand you need a high quality counter which is able to deliver the resolution and the sensitivity to do those jobs. Okay, so we are now approximately a half an hour ahead, and it is still very good, even with the lid on. So let's simply put it to the other counter to compare it, but both counters are on the same standard, so that won't be a difference. But let's do it just to see what we get. So now let me take the wire from my Agilent counter over here to my Racal. Let's see if the Racal can do the same, and it can. So you see that it is approximately on the same frequency. So that you see that is 1 kilo, 100 hertz, 10 hertz, 1 hertz, and that is 0.4. So 0.6 hertz off for the moment in time, which is a very good value for a reference oscillator. So no problem whatsoever. Okay, and if your ears are trained, you may hear that now the receiving tone is already fine, and it is really only 13 hertz off. So that is allowed. So 30 plus minus 30 hertz is allowed. So that is now on receive. Now let's see what it would mean on transmit. So let's see. So we do exactly the same procedure. So on SSB, let's see what it is. Now we go on transmit, and you see we are only 8, 9, 7 hertz off. So the level is a little bit too small. Where is my mic amplifier? So as I told you, what we need is 7001 because our 1 kilohertz audio. So we are at the level is a little bit too small. I'm only transmitting into the radio with 1.3 watt, and that means that our, let me increase it here a little bit. Now it should get more stable, and not really. And you see it is only it is only let me take my attenuator off in between, because the level is so small. Maybe that that will help. Let's see, hopefully. So you see that really we are only quite a bit off without any problem, and that is fine. So what is it exactly? For the moment in time it is 9 hertz, it is 10 hertz, so maximum 10 hertz too low. And again, that is absolutely in tolerance. So allowed tolerance is plus minus 30 hertz, and therefore that is excellent. So we really do not need to do here anymore. So nothing to complain so far. Very good. So basically we could really stop here, because we are already in frequency, and the frequency error on 2 meter or down on shortwave would be even smaller. You really wouldn't really recognize the error. So when it is fine on 70 centimeter, it is definitely fine on lower frequencies. And therefore, so we have seen maximum we are 10 hertz off, which is fine, and we have done it here. But because we are working on SSB, we have a second oscillator, and that is here the carrier reference adjust for our 2 carrier DDS oscillators. So we have an RX carrier DDS oscillator and TX carrier DDS oscillator, which both rely here on our carrier oscillator. And you see it is going to the TX DDS carrier oscillator, and it is going to the RX carrier DDS frequency oscillator, and we need to bring here our Bose reference frequency, not the Bose, the one reference frequency for Bose DDS oscillators. We need to bring them in frequency as well. So that is what we do, but we stop the video here because it is the same procedure and it would extend the video much too long. But I am going to show you where our reference oscillators are. So this here, our DDS oscillators, and you see here another crystal, and that is a crystal, the reference crystal here for our Bose RX and TX DDS oscillators, and therefore we improve here our reference frequency as well, and then it should be even better. But anyways, you have seen we are already in tolerance, so normally we wouldn't need to do anything, but I wanted to make sure that our carrier oscillator frequency for SSB is also fine. All right, so but as I said, I stopped the video here. Thanks for watching. Catch you next time. Bye.